Okay, good morning everyone. Today is a lecture on content-based recommendation and quite familiar material based upon what we saw when we talked about information retrieval and search engines back in the early part of the term. So up until now we've looked at collaborative filtering by virtue of the user providing us with feedback that was almost directly usable, or we could infer if we were using sort of clicks or time spent on a page. But what you're doing for assignment 2, of course, is using the actual content, and I've tried to focus your attention on a use of sentiment to get some kind of rating. But we've also been interested in inferring things in terms of topic models, and that's where both the latent Dirichlet analysis and, to a lesser extent, singular value decomposition have been useful. But it's also possible that we might want to use the content directly, and we've seen that before. We will then use that material as direct use or direct implication of user preferences, and then we're going to use that model, that vector space model, to determine who's similar to us, Alice, Bob, as we've done before. So we're going to take the user profile, some contextual information. If we were doing all kinds of recommendation across demographics, then we might take information that we knew above and beyond actual content into account, along with the features that we have about the material itself, run it through our black box and get a recommendation. So the content here is the actual page itself, and in the case of the assignment that you're doing, that's the actual web review. So we can use that as a document, much in the same way as we did when we were creating our search engine, where we can look at either an extraction of the material in terms of particular keywords that we see there, or just the raw text itself, which we did back in probably lecture 5 when we picked up things that were inside of paragraph tags, inside of H1 tags, and so on. If the user has nicely annotated things in terms of keywords, or we have this structured model that you can see in the table where we have metadata such as author and title, and if we're really lucky, things like genre, which we might get from a product catalog, then we can use that directly in terms of the construction of a content model. So those attributes, if we're lucky, are given to us. If not, we might try and infer them using some kind of topic model or some other type of classification mechanism that we won't talk about in this particular course, but you would certainly in a machine learning course. What we're going to do is to talk about more about content as we move forward. But let's imagine for a moment that we do have a tabular description, something obviously with columns that are labeled, something we could actually get from a catalog such as Best Buy. We'd be able to get price, we'd be able to get type, some sort of category. If we were analyzing a bookstore, we would be able to get obviously title, genre, author, type, price, and possibly keywords. But then we would also have a user profile, where things like genre, author, paper book, some sort of price sensitivity and keywords might be specified for us. And then in order to try and infer whether a user is actually interested in this particular item, we perform some kind of similarity calculation where we would look at literally the common keywords and normalize it by the number of keywords which are actually in particular user or book profiles. So this kind of similarity measure would allow us to decide whether an item was of interest or not. What we'll find is that we may also want to combine multiple metrics, namely things which are in particular fields, to use the Lucene terminology. So in terms of those columns that we see, genre, author, etc., and the keywords, in order to decide on whether something is similar or not. We don't have to have a simple single metric comparison. Here on slide 4 we see a single keyword based comparison, but we could imagine looking at other columns which you can see also contain the possibility for a keyword based comparison. And finally, we have a numerical value such as price which we can compare as well, and that will be relevant when we talk about knowledge-based recommendation in the next video. So here we've got the item representation which we can compare as well. We can compare by constructing some sort of vector representation for both item and user. The thing about keyword extraction is, as we've seen, it doesn't always have the same importance. If a word is used everywhere, it really hasn't a great deal of significance, and word sensitivity is clearly something that has a dependence on a user. But we've seen that we can solve some of these problems that are not user-based, but they are document-based, by using TF-IDF. And so I'm going to go through this particularly quickly because it's in the nature of review from earlier on in the term. So TF-IDF gives me an ability to encode documents in a multi-dimensional space. That dimensional space is the size of the vocabulary that I choose to extract from the document corpus that I have available to me. And so I have something which allows me to weight particular terms based upon their frequency of usage, both within a document and across the entire corpus. So the term frequency is the density in a document, and the IDF, the inverse document frequency, is there to show whether or not the term has significance with respect to it being rare. So IDF has these terms. So I've got a term frequency of a keyword I in a particular document J, and then inverse document frequency is just the log of the number of documents in which that particular term is to be found, and that's the number of documents over this particular frequency. People will normally include a normalizing value in this particular case, because you don't, if n of I is 0, that blows up IDF. So people will very often make sure that that IDF term doesn't. So you'll see a +1 somewhere in many of the books that describe this particular material. So TF-IDF is just the product of those two factors, and you did that kind of calculation in a small document corpus earlier on. Here's the classic example. I won't really go over this. If you want to actually go through it, it's on Wikipedia. You can also go to informationretrieval.org. It's also in the slides from earlier on in the term. So I've got a count vector for a particular term. A term doesn't actually have to be a single word. It can be, as you can see here, Julius Caesar, which is obviously a proper noun. Julius Caesar is the document here, and the terms which I'm extracting are Antony, Brutus, Caesar, Calpurnia, Cleopatra, Mercy, and Worsa. And you can see then, because I'm extracting my vocabulary of 7 words, I've got a dimension 7 vector. So each one of those can be then changed into a TF-IDF weight. And so the vector describing Julius Caesar would be, as you can see, column 2 there, 3.18, 6.1, 2.54, 1.54, 0, 0, 0. And you did that kind of work back in lecture 7-8. They're usually sparse. You will see that in your review analysis, if that's what you're doing for assignment 2. We typically remove things that have no value, things like a, the, and on, and those are referred to as stop words. We do stemming because particular words, there are many variants effectively of the root word, the stem. Things like the verb to be. Clearly we don't want to consider all words deriving from that particular verb as independent when I'm just looking at information content. So I will stem those to, as you can see with the examples here, went being reduced to go and stemming to stem. Similarly, plurals are also something that we reduce to the root form, so the singular form. Because we don't want these vector spaces to have too high a dimension, or if we do, then of course we could project them into a lower dimension using singular value decomposition. We would choose possibly to cut off the use of those representative words at some value of n. Here on this slide, it's chosen to be 100 words, but if you were to do analysis of the review documents, the vocabulary that's present in those documents is quite large, and without stemming and stop word removal, you end up with a very large multi-dimensional space. Just for your interest, the standard analyzer, which is inside of Lucene, obviously does something based upon a bag of words where you've got a predetermined vocabulary. And you might well be considering the use of that standard analyzer to analyze the reviews. So don't think of assignment 2 as just using one particular tool to come up with a design. You have a very large number of tools that you can bring to bear on analysis of that particular data set, which, as many of you have asked me questions about, is quite complex. So we can improve that very, very basic vector space model. In today's world, we might even use some kind of neural network to perform word embeddings, and some of you may have heard of word2vec. We won't discuss those here, but there are very, very many ways in which these document-based analysis tools can be augmented. The TF-IDF can be augmented. We can remove things, words that we know are absolutely not relevant to our domain. We can obviously have more than just simple tokens that we extract. So United States of America would obviously be something we would want to extract. United Nations, as an example, well, would be something we would want to extract. But nevertheless, if we just look at simple syntactic analysis, that really limits what we can get out of the document. Word2Vec, for example, uses this idea of words have certain associations, i.e. their distance from other words is relevant, and clearly TF-IDF doesn't capture that. But semantic analysis is something that people do as well, and to some degree that's what topic-based analysis does for us. It introduces this intermediate model, these latent features that are themselves descriptors, vectors of words. So they extract the associations between words in order that documents are partial representatives of topics. And so if you don't remember that particular lecture, I suggest that you go back and review it. Extracting negative connotations is something we've discussed for sentiment, and the very, very basic algorithm which was presented to you in naive Bayes solved the semantic problem by basically creating new words that had the word not in front of them, where the phrase, the whole phrase of words, which was being given a negative connotation. We did that because we were interested in computing sentiment. And so often you will annotate your original corpus of words to include the semantic you're trying to extract. Here in the naive Bayes for sentiment, we just prefix the word with not. In a more sophisticated technique, we would actually use some kind of neural network which would analyze the phrase themselves. So we would do some kind of sequence analysis in order to be able to predict that a phrase had a negative or other connotation. So you can see here that the example is that the word vegetarian and not, there is nothing on the menu that the vegetarian would like. Here we're trying to imply that the restaurant for which this review was created would not be something that a vegetarian would like. And that's a very difficult thing to extract from that phrase, but you and I as human beings are totally capable of doing so. So in this particular class, we're interested in use of TF-IDF. We're interested in the use of simple annotations of words to create new words to get sentiment, for example, but there are a very rich set of other techniques which we can't discuss here because of the time constraints. Once we've got our vector models, we can compute similarity, and this was discussed in lecture 7 and 8 with the use of Lucene and the use of creation of vector space models. And we've used two forms of cosine similarity in this course. One was the direct one, which we used back in 7-8, lectures 7-8, and is shown at the top of this particular slide. And we used adjusted cosine similarity a few classes ago when we were looking at user similarity when you essentially had two types of user. You know, pessimistic users who would have low average rating, and you have optimistic users who would have, on average, a very high rating. But they are similar because of the trends in their rating behavior. And that's why we would choose to use them in computing a recommendation. So we do use similarity, sometimes offset by some average, and sometimes they use the absolute value. That's what those two forms are present. Once we've found things, we look for neighbors. And neighbors, we found that we are interested in looking at clusters of things. And that's why we studied cluster analysis. But of course, we can always, given a representation of a user, find the n nearest neighbors that have either liked or disliked a set of documents. So we can compute these clusters of what we think are like items, and then we can, given a user or an item, decide where it should go. We can decide, if we're looking for like users, find like users within a cluster, and then use their preferences in order to create recommendations for the user that I'm currently interested in. So you can see here I'm going to take the neighbors to predict an item. We saw that a couple of classes ago, and we are here looking at whether or not the items were liked or not liked. But the thing about this is that if you only include like, then you are, if you follow this to a logical conclusion, you only ever focus a user on liked things. You never expand their interests with respect to things that they have not seen, and that itself can be a problem. But you play with these values in terms of neighborhood size, similarity thresholds, and so on. But they still have limitations with respect to not expanding the user's interest in things that they have really never seen. So what we want then to do is potentially introduce novelty into the things which are retrieved for a user. And Roccio's method allows us to do that. So the smart system, users can rate relevant, irrelevant things in terms of what was retrieved for them. And then in this system, queries are automatically extended with extra terms in order that we can end up with a mixture of things which are relevant and potentially historically irrelevant. So the details of the algorithm are really quite simple. So imagine that we end up with two sets of documents, both liked and disliked, D plus, D minus. What we do is we form a query that is a blend, if you will, of the two queries which would constitute retrieval of the centroids of those document collections. So we do clustering in order to compute these collections. Then we are potentially combining the queries which would result in the centroids of D plus and D minus, and then retrieving the documents which are part of that blended query. There are a number of hyperparameters here, alpha, beta, and gamma. These are typical values. In this case, they don't include the documents that have negative feedback, but if they were, you would imagine that the novelty introduced by those negative feedback documents would be quite small. But the purpose of adding in that query component is to introduce novelty. Because remember, irrelevant or non-relevant documents may not always be so. Our interests do actually change with time, and we do want to get out of this sort of valley, if you will, of always getting back the same content. We want there to be this capability of introducing novelty as we go forward. So that query that you see there, so if I've got the current query, there are three components then that I have in the query that I am going to use inside of my system. There's the query itself, and that's going to be weighted. Then there's the query which is essentially dealing with the centroid of the relevant documents which have historically been retrieved. And then there's a component which is being subtracted, because remember, these are representations in document space. They are not representations in word space. So I am assuming here that my document is represented by some TF-IDF vector or some other representation. It could be a topic-based representation. It doesn't matter. But the query is intended to have been transformed into that space, and then the centroid of clustered documents and clustered disliked documents are used to modify the query, and the results of evaluating Q of I plus 1, the modified query, is the set of documents that the user will see, and now ranked in the usual Lucene-like way. It can, to use this model, you require like-dislike from users, and that's its biggest kind of limitation. But imagine that you have review, right? A document here has been is a movie. The feedback, you know that they've actually accessed it, right? Because they have generated a review on that document, and so you can actually then use that as some kind of feedback. You can say, oh, it was negative sentiment, therefore it was a dislike. We'll put that in a different set. So we can do that. We can use Roccio's method in order to refine our vocabulary too, and that is done, but that's more of an advanced concept which, for the purposes of this particular lecture, we won't consider. But Roccio's method is used to introduce novelty. It is designed so that you're not stuck with the same old response all of the time. And this is somewhat different from search, where I only wanted some kind of keyword model to define my response. Here we are looking at recommendation, and recommendation is in part providing feedback to the user that comes from that long tail. And if you don't know what I mean, go back to the very first Recommender 1 lecture and look at the early slides. And also go back and review Andrew Nye's lecture, which was also part of the first lecture suggested review material. So we can use also content. We can use probabilistic methods to do actual evaluation of whether something should be reviewed. And this calculation is very, very similar to the naive Bayes calculation that was done to compute rating a while ago. It's just that now what we are doing is reducing the calculation. Instead of on a Likert scale of 1 to 5, it's 1 to 2. And the calculation that you see on this slide is really identical to that calculation. So what's the probability that it's going to be hot or cold based upon whether the particular document had a particular value. So we reduce the frequency of our keyword in a document to 1 or 0, much as was done with sentiment, and then given its label, we are saying whether it was liked or disliked. We can compute the probability of a document being liked or disliked using a naive Bayes approach. So this calculation here is identical to the calculations that have been done inside of the naive Bayes calculations for sentiment. And so I'm not going to review that here. If it's unclear, go back and review those slides between about 20 and 27 of the sentiment-based lecture. It's also possible to try and separate documents into two classes as to whether they'll be liked or disliked by drawing a line or a plane, in the case of multiple dimensions, between two classes. And linear classification can do that. We're not studying that in this particular course, but a more sophisticated form of classification could be performed by a neural network. For example, once we have again reduced our documents to TF, IDF, or other embedded forms. So the task would be to convert all documents to their vector space models, feed those to some form of classifier. Let's imagine it's a neural network. The output of the neural network would be a like, dislike for irrelevant for a particular user, and assuming we've got enough examples for a particular user, it would then thereafter capture the user's particular preferences and predict like, dislike for them given a new document, and that document would be the embedded form of the document. And that type of classification process would actually be fairly straightforward to do. Linear regression could be performed in order to compute this kind of hyperplane, which we won't talk about here. Assume that you can do classification based upon naive Bayes, which you've done based upon sentiment. And you can use Rocio's method to introduce diversity into the resulting documents which are retrieved and recommended to a potential user. Bullet 2 here really indicates the simplistic nature of TF-IDF. It doesn't really associate positional dependence on keywords, and given that we're reducing everything to like, dislike, then the keyword counts are lost. Again, go back to the sentiment algorithm and you'll see what I mean. The algorithm roundabout slide 25, 26 really, first of all, reduces the frequency counts of all of the words in your dictionaries to 1, and you end up with 2 documents, one containing all of the words which are positive and all of the words which are considered negative. We can include in these probabilistic calculations the frequency, and that was alluded to in the sentiment slides as well. But again, we won't discuss that. There are lots of other machine learning techniques that are more sophisticated, that are beyond the scope of this particular course. Then finally, we can add in all kinds of extra factors. Search engines, such as Google's, that uses brain rank and other things, use very, very sophisticated extra features to determine relevance. It isn't simply based upon content. We know it's based upon structural interactions, the graph of connections between web pages. That can be used too. So this is where I kind of stop for this particular course, because it would require us to move into machine learning. But slides 19 and beyond are interesting in if you wish to go on and study this on your own time, but are not included in this particular course. So with that, the content-based portion of this particular course is done. Thank you.